Hi, I am Shreyan Soni, and this is my submission for CS7GV03 Assignment 3 on normal mapping. In this demo, I'll demonstrate both bump mapping and normal mapping in GLSL on multiple rotating objects. Here's my scene with three rotating models demonstrating normal mapping. On the left is Suzanne, center is a cube, and right is a manhole cover. All are rotating to show how normals affect lighting from different angles. What are normal maps? Normal mapping is a technique for adding surface details without additional geometry. Every surface in 3D graphics has normal vectors, directions perpendicular to the surface, that determine how light interacts with it. A normal map stores these normal vectors as RGB colors in a texture. Red encodes x-axis direction, green encodes y-axis, and blue encodes z-axis. That's why normal maps look purple-blue. The blue channel represents normals pointing outward from flat surfaces. With normal mapping disabled, you can see flat surfaces with no details. The lighting is uniform because it only uses vertex normals. With normal mapping enabled, surface details appears. Grooves, bumps, scratches. The geometry hasn't changed at all. We simply use per pixel normals from the texture instead of interpolated vertex normals. Normal maps are stored in tangent space, a local coordinate system for each surface triangle. The z-axis points away from the surface while x and y lie flat along it. My shader transformed these tangent space normals into world space using TBN matrix tangent by tangent normal. The TBN matrix is built from tangent and bitangent vectors computed by ASIM during model loading. This transformation ensures the normals work correctly regardless of the object's orientation or rotation. The assignment requires demonstrating bump mapping as well as normal mapping. In my implementation, bump mapping is controlled through a strength parameter. After decoding the normal map, I scale its XY components, the tangent and bitangent directions, by bump strength value. This controls how much the normal deviates from the flat. At zero bump strength, normal points straight out, completely flat. As I increase it, surface detail become more pronounced. At maximum strength, the bumps are exaggerated. This is the essence of bump mapping, using the normal map data to create adjustable surface perturbations without changing the underlying geometry. The power of normal mapping comes from how these per pixel normals interact with lighting. Watch what happens when I move the light source. The surface details respond dynamically. Bumps appear to catch light and cast shadows, even though geometry is perfectly flat. The normal vectors determine how much light per each pixel receives. Normal mapping works with any lighting model. Here it is with smooth lighting and here with cell shaded toon lighting. The surface detail is preserved in both cases. Notice how specular highlights follow the surface details. The normal map directly influences where highlight appears, creating the illusion of three-dimensional surface features. To summarize, I've implemented tangent space normal mapping with adjustable bump strength in GLSL. The technique adds detailed surface features to low poly models through per pixel perturbation. Multiple rotating objects demonstrate the effect from various angles. Thank you.